Okay, good afternoon. I want to spend a little bit of time talking about the right-hand rule because the right-hand rule comes up a lot in Chapter 5. In fact, there are 3 separate applications, and I want to go over each of those applications. Before, I just want to warn you that if you go and look on YouTube or elsewhere, then you might find a different application of the right-hand rule, that different people just sort of do it differently. And, just try to follow my example, and then it'll be a little less confusing. Or if you decide to choose somebody else's example, just be consistent in that. Either way is going to be okay. But it all comes about from the cross product. So if you've ever had Calculus 3, or maybe Calculus 2, you might have gotten into the cross product. You might remember cross product from last semester when we talked about torque. We said that torque was equal to RF sine theta. But torque is actually a vector quantity. You remember this? Where we said that the torque is actually equal to the cross product of R and F. And it turns out that these two are identical, that the magnitude of the cross product of the torque is RF sine theta. And the cross product, you have 3 vectors. In today's application, we're going to be looking at F equals QV cross B. We have 3 vectors. This X looks like a multiplication sign, but it means a lot more than that because you're actually multiplying 2 vectors. You're taking the cross product. These 3 vectors are orthogonal. Orthogonal is just a fancy way of saying that they are all perpendicular to one another. Just like the XYZ axes are orthogonal, these 3 vectors are all orthogonal. Now, we use our right hand and the fingers in this orientation with our thumb pointing up like we're hitchhiking, our index finger pointed out like you're pointing at somebody, and then your middle finger, well, I don't know what the middle finger would be, but we use our hands in this configuration because you can see that these are all at 90-degree angles to one another. These fingers are all orthogonal, and so they help us to think about if I have 2 vectors in 2 directions, then what's the direction of that third vector? The way that we're going to do this is a lot like this, where I have this sort of generic cross product for A and B. Except now, instead of A, we're going to let that be our vector V. Instead of B, we're going to let that now be our magnetic field. And then over here where I have the cross product, that's going to be our force vector. So let's do an example. By the way, when you're calculating the force, we don't do cross products in this class, we just find their directions. You're going to be doing QVB sine theta. That expression is equal to the magnitude of our cross product QV cross B. So this is what I gave you in the notes, and that's what you'll be using. So let's do an example. We'll do a simple one. Let's say that I have a positively charged particle moving with this velocity in that direction. So I start with having my index finger point to the right. Everybody, take your hand and point your index finger to the right. Now, you might have your thumb and your middle finger out, but you don't know at this point how they're going to be oriented. All you know is that that index finger has to be pointed to the right. Do you see how you can rotate your hand around so that your index finger is always pointing to the right? Now, if we know that the magnetic field is, say, in this direction, then we orient our hand so that our middle finger is pointed downward. So starting with your index finger to the right, rotate your entire hand around until your middle finger is pointed in the same direction as B. And then you ask yourself, what is the direction that my thumb is pointing? What is the direction that your thumb is pointing? It's pointing into the page. So my force here is into the page. Let me give you some symbols here. I have the symbol X and dot. X means into the page. Sometimes I'll use an X. Often I'll draw a little circle around it. And a dot means out of the page. By the way, these are also my minus Z and my plus Z directions. I gave you this in the notes. So, F being into the page, if I were to draw that vector, my force would look like that. Okay, let's do another one on the next page, and then I'll show you some of the other examples. So, let's say that my positive particle, that's very important, by the way, the sign of the particle, and I'll explain to you in just a bit why. The positive particle is pointed upward. Then this is the velocity, is going upward. And now let's say that the magnetic field is into the page. And the way I'm going to draw this is I'm going to say the magnetic field covers this entire region. The magnetic field, which is in red, is into the page. So my velocity is up. Take my index finger and point it in the same direction as the velocity. Now I need to rotate my hand so that the magnetic field is into the page. So that's your middle finger should be pointing into the page. And then my thumb will be pointing in the same direction as the force which is acting on that particle. What is the direction that your thumb is pointing? Well, I know it has to either be left or right because it has to be orthogonal to both vectors that I have already. So I have one vector that's pointing in the y direction and another vector that's pointing in the negative z direction. So this vector for our f has to be either plus x or minus x. Which do you think it is? It's going to be minus x. So my force is in this direction. Let's try another one. I'm going to do a little more difficult one this time. So this time I'm going to have a positive charge. Let's say that my force is up. I'm giving you the force now, and so you're going to have to approach it a little bit differently. Let's say that my magnetic field is, let's see what I do. I'll do red. Say my magnetic field is to the right. So force is up, magnetic field is to the right. Now what is the direction of the velocity vector? So remember, your velocity vector is your index finger. Right? This is velocity, this is magnetic field, and then this is force. So I point my thumb, you can start with either one, it doesn't really matter. I'm going to start with my thumb, let my thumb go in the direction of the force, because my thumb represents the force. Listen, if you want to go out, I can't stop you from getting tattoos. If you want to go out and get F tattooed on your thumb, V tattooed on your index finger, and B tattooed on your middle finger, you go right ahead. Okay? So I'm going to let F be pointing up. My thumb will be pointing in the direction of F. And then my middle finger will be pointing in the direction of B, which is to the right. Now, which axis is not yet occupied? F is in the y direction, B is in the x direction, so the z-axis is not yet occupied. That means that V has to either be plus z or minus z. Which do you think it is? Well, with my thumb pointed in the direction of F, my middle finger pointed in the direction of B, and with my hand oriented like this, that means that the velocity has to be in the plus z direction. So that would be like this. So my velocity vector would be coming out towards you. So this charge is traveling out of the page and towards you. Let me show you another application. This application is actually identical to the one that I've shown you already. Remember, so F equals QVB. And I'm letting this be my thumb. V is my index. And B is my middle finger. And we're going to do this over here again. So this is V, this is B, and this is F. There's a very similar application when I have a current traveling through a wire. And the equation for this, which we haven't seen yet today, but we'll see it on Wednesday, the equation is F equals I L B. And actually there's a sine theta term, but F is equal to I L B. We're going to Let's make a little aside right quick. So I is a scalar. Current is a scalar quantity. L, which is the direction and length of the wire, that is a vector. So imagine that I have a wire right here. The direction that it's pointing and the length that it is, that is going to be my length vector. And then B is also a vector. We don't usually think of a length of a wire being a vector quantity. And so it's a lot easier to talk about direction when we talk about the direction of the current. Because even though current's a scalar quantity, it has a direction. So happens that the direction is the same as the direction of the wire, right? Because it's constrained to the wire. So when I talk about this, I'm going to be talking about the direction of the current and not the length. So I want you to remember that really it's the length that's the vector quantity, not the current, because current is a scalar quantity. So I would have here F is going to be my thumb. I is going to be my index finger. And then B will be the same. It'll be my middle finger. So imagine that I have a current carrying wire. Say it has a current going in that direction. Let's say that it's going through a magnetic field that is out of the page. So these blue dots represent the magnetic field coming out of the page towards you. The dot is like an arrow that's flying towards you. It looks like a dot. The X is like an arrow flying away from you. That's the fletching on the arrow, the feathers on the back of the arrow. And then I want to know what is the force on this. So I let my index finger go in the direction of I. I let my middle finger go in the direction of B. And then my thumb will give the direction of the force on the wire. Try that out and see what you get. Now remember, I is in the plus X direction, B is in the plus Z direction, so that means that the force has to be either in the plus or minus Y direction. Which do you think that it is? It's going to be in the minus Y direction, so the force is in this direction. Index finger in the direction of I, B is out of the page, and so the force is pointing downward. Okay, there's a third application of the right-hand rule. I'm going to go ahead and do it. It's going to be a couple of days before we get to it. Let me go ahead and show you. It's called the curl rule. I think people are pretty standard on how they do this. The curl rule just says if I have a wire like this, there's a magnetic field that goes around it. Imagine this wire that you're looking on end so that the wire is coming towards you. So here you're just looking at the tip of the wire as it comes out of the page. The magnetic field that surrounds this wire will be like this. There'll be a magnetic field that will emanate outward. It'll get weaker as you get further away from it, and we'll talk about that later. But the magnetic field goes around the wire in a circular pattern. One of those clips, I think it was the Veritasium clip that I had for you, showed this, where the relativity about where that actually comes from. But the magnetic field will go around this wire in a counterclockwise fashion. Now, let's imagine this wire here. For this wire, the magnetic field is going to be into the page on this side and out of the page on this side. The magnetic field is into the page on the right and out of the page. And so if you imagine this magnetic field is going to be going around the wire in a circular fashion that sort of comes out of the page, into the page, out of the page, into the page. I do this with the right-hand rule. I let my fingers go, or let my thumb go in the direction of the current. And then the fingers wrap around to give the magnetic field. So my current is in this direction, and then my fingers wrap around to give my magnetic field. So my magnetic field will always be into the page on this side and out of the page on this side. Imagine, what if I had a wire that was like this? What would it look like? Well, it would be similar. It would be into the page on this side and then out of the page on that side. We'll see that more as we get to it. People usually find that this is a little bit simpler. We'll see some different other applications of these same right-hand rules, but these 3 right-hand rules, and really it's just 2 right-hand rules because the first 2 are basically the same. These 3 right-hand rules are going to be really important to this chapter. So please spend some time practicing these. There are lots and lots of test questions for you to go through and review and practice. Okay, I'll see you Wednesday.